Hi, in this video we are going to see how we calculate the Fourier transform of periodic signals. Now we remember that any periodic signal which is absolutely integrable over a period has a Fourier series representation. So we are going to use the Fourier series representation to calculate the Fourier transform. Now we know that in the Fourier series representation, the signal is expressed as a superposition of harmonically related complex exponential signals. Therefore, we have to start with the calculation of the Fourier transform of the complex exponential signal. So, let us consider the complex exponential signal x of t equal to e to j omega 0 t, where omega 0 is the angular frequency of the complex exponential signal. Now, can we calculate the Fourier transform of x of t by using the Fourier integral? Unfortunately, the answer is negative because x of t is not absolutely integrable. Now, we look at the integral from minus infinity to plus infinity, x of t, magnitude x of t, integrated with respect to t. Here we have a complex value signal, so the magnitude is the modulus. And modulus of e to j omega 0 t is equal to 1. So this is the integral of 1 from minus infinity to plus infinity. But we know that this improper integral is divergent. So this is a divergent integral. Therefore, x of t e to j omega 0 t is not absolutely integrable. So Fourier transform of e to j omega 0 t does not exist. In the classical sense. Now, in terms of the Fourier integral, we cannot calculate the Fourier transform of e to j omega 0 t because the integral will be divergent, and therefore the Fourier transform does not exist. Let us remember what we mean by the existence of the Fourier transform. The Fourier transform exists provided that x of omega in magnitude is always finite for all frequencies. Therefore, in this case, we will not be able to find a Fourier transform which has a finite magnitude or bounded magnitude for all frequencies. But we are going to see that the Fourier transform of this signal can be expressed in terms of the impulse, which is a singular function, remember, which has infinite magnitude at a certain point. where the impulse is defined. So how do we obtain that result? We can use the inverse Fourier transform to obtain a Fourier transform of e to j omega 0 t in a generalized sense in terms of a singular function. In terms of a singular function, namely the impulse function or Dirac delta function, as follows. Now, remember that we can obtain, if in general we have the Fourier transform pair x of t and its Fourier transform x of omega, x of t can be obtained from the Fourier transform expression x of omega by means of the inverse Fourier transform expression, which is 1 over 2 pi from minus infinity to plus infinity x of t e to j omega, sorry, it is not x of t, of course, x of omega, because we are trying to find x of t from x of omega, e to j omega t integrated with respect to omega. So, let us see how we obtain e to j omega 0 t from now x of omega. Here we are going to write down the expression of x of omega multiplied by e to j omega t, and we are going to integrate with respect to omega, and we will obtain e to j omega 0 t. Obviously, the expression we have to substitute here is 2 pi, because 2 pi's will cancel out, delta of omega minus omega 0. So 2 pi's will cancel out, and remember the sampling property of the impulse. Delta of omega minus omega 0 multiplied by e to j omega t and integrated with respect to omega will sample e to j omega t at omega equal to omega 0. Therefore, we have obtained Fourier transform of e to j omega 0 t as 2 pi delta of omega minus omega 0. Now here, it may seem that we have used some contradictory discussions to obtain this result. First of all, we have started with the expression and tried to use the Fourier transform integral directly, and there we have observed that e to j omega 0 t is not absolutely integrable, therefore the Fourier transform does not exist. But then, by a different argument, we have obtained the Fourier transform. But this is not a contradiction. We remember the following. By the existence of the Fourier transform in the classical sense, that means we are able to calculate the Fourier transform from the Fourier integral, provided that the signal is absolutely integrable, and as a result of the Fourier transform, we obtain a function x of omega, which is bounded for all omega. its magnitude is bounded. It's finite for all frequencies from minus infinity to plus infinity. Here, as you see, we have obtained the Fourier transform of e to j omega 0 t as an impulse. And we remember that the impulse is infinite at omega equal to omega 0. So the Fourier transform is in fact now a singular function, which is 0 for all frequencies except the frequency omega 0, where it is infinite. So this is really in harmony with what we have asserted at the beginning related to the existence of the Fourier transform. We have obtained the Fourier transform, but it is now a singular function rather than the well-behaved Fourier transform of absolutely integrable signals. In that case, the Fourier transform has a finite magnitude for all frequencies from minus infinity to plus infinity. Okay, now let us see an example of this result, or an example related to this result. For instance, x of t is cosine t. Let me call it x1 of t, cosine t. So x1 of t can be expressed as 1 over 2 e to jt plus e to minus jt. And by using the linearity of the Fourier transform, we can calculate the Fourier transform of these two complex exponential signals and superpose them. So x1 of omega is 1 over 2 2 pi delta of omega minus 1 plus 2 pi delta of omega plus 1, or pi delta of omega minus 1 plus pi delta of omega plus 1. So we have the two frequency components with frequencies 1 and minus 1, and therefore we have these two impulses located at omega equal to 1 and omega equal to minus 1. Similarly, x2 of t is, for instance, sine t. So it can be written as 1 over 2 j e to jt minus e to minus jt. So x2 of omega is pi over j delta of omega minus 1 minus pi over j delta of omega plus 1. Again, we know that in the real valued signals, periodic signals, cosine and sine, we have two frequency components, the positive frequency component and the negative frequency component, because we know that for periodic real valued signals, whatever you have for positive frequencies, you have a counterpart at negative frequencies. How we interpreted the necessity of negative frequencies in the representations of real valued periodic signals. So next we are going to try calculating the Fourier transform of a periodic signal, a general periodic signal with a certain Fourier series representation. by using the linearity property of the Fourier transform, we are going to calculate the Fourier transform of the Fourier series in terms of the Fourier transforms of the complex exponential signals which are superposed. So let us now look at this problem. Okay, now let us consider a periodic signal. X of t is a periodic signal with a fundamental period capital T0 with the Fourier series representation with the following Fourier series representation. X of t is equal to k from minus infinity to plus infinity, ak e to j k omega 0 t. Now, Fourier transform of x of t in terms of the Fourier integral again does not exist because x of t is not absolutely integrable. So, we know that from minus infinity to plus infinity, magnitude of x of t integrated with respect to t is divergent. So, Fourier transform of x of t does not exist. By the existence of the Fourier transform, we mean a Fourier transform expression which has finite magnitude for all frequencies. But again, in this case, we know that x of t is expressed as a superposition of complex exponential signals, and each complex exponential signal is again not absolutely integrable, but it has a Fourier transform which is a singular function, which is an impulse, which has infinite magnitude at a certain frequency. So we are going to make use of that fact. However, we can calculate a Fourier transform of x of t in terms of singular functions. So we will have an expression containing infinities. Okay, so we follow the following steps. The first step is Fourier transform of e to j k omega 0 t is equal to 2 pi delta of omega minus k omega 0. Here omega 0 is of course related to the period t0 by this expression, so I have to write it here. Omega 0 here is 2 pi over t0, so t0 is the fundamental period and omega 0 is the fundamental frequency. And the next step is using linearity of the Fourier transform of the Fourier transform Fourier transform of x of t is k from minus infinity to plus infinity, ak 2 pi delta omega minus k omega 0. Okay? So the Fourier transform of a periodic signal can be obtained from the Fourier transform of the Fourier series expression in terms of course, singular functions in omega domain. That means we have infinities at omega domain at the particular frequencies, which are integer multiples of omega 0. Okay. For example, in fact, we have seen the cosine and sine signals. They are also periodic signals with the simple Fourier transforms containing only, Fourier series expressions containing only two terms, and the Fourier transform can be easily calculated. But in the general case, we have this expression. So, let me give an example here. X of t is from minus infinity to plus infinity, delta of t minus m t0. So this is our impulse train signal. And we have calculated the Fourier series as x of t equal to k from minus infinity to plus infinity, 1 over t0 e to j k omega 0 t. Remember, in the impulse train, the Fourier series expression of the impulse train, the Fourier coefficients are all equal to 1 over t0. So we interpreted this as something related to the singularity of the signal. All frequency components are represented with equal weight. So in this case, x of omega turns out to be k from minus infinity to plus infinity, 1 over t0, and then we have, by using the linearity of the Fourier transform, the Fourier transform of the complex exponential signals, which is 2 pi delta of omega minus k omega 0. So here in the Fourier transform expression, we see that the Fourier transform is 0 everywhere except the frequencies which are integer multiples of omega 0, and at those frequencies the Fourier transform is infinite in magnitude, which is related to the fact that the periodic signal is not absolutely integrable. Therefore, the Fourier transform does not exist in the classical sense in terms of the Fourier integral. We are not able to calculate it from the Fourier integral, but we can calculate it in terms of a superposition of the impulse functions, which are singular functions having infinite magnitude at certain at the points where they are defined. Okay, thanks for watching.